Welcome to the set of lectures on Hamilton-Jacobi equations. So we'll be discussing some aspects of Hamilton-Jacobi equations which has applications from calculus of variations, which is a pretty old subject. It has a more advanced topics like Hamilton-Jacobi-Bellman equations and Hamilton-Jacobi-Isaacs equation. We will be doing very little in this course because this is a nonlinear type equations. There's a lot of literature and lot of modern techniques are available to study the general Hamilton-Jacobi-Bellman equations. Our main aim is to derive two things, to study two things. One is a representation formula called Hoflach's formula, and then we will do a little of derive the Euler-Lagrange equations corresponding to that, and then we also connect what are the two terminologies, what are Lagrangian and Hamiltonian. These terminologies are drawn from the usual classical mechanics, and we will give a connection between the Lagrangian and Hamiltonian via the Legendre transformations. We will also introduce the concept of some weak solutions and nonlinear equations. We will give examples. Will not produce existence of solutions. Sometimes there will be multiple solutions, and then you have to choose when you have a multiple solutions, you have a right notion of solutions and right conditions to pick up the correct solution. So we will be doing this in 3 hours and 5 to 6 hours, and we'll do the minimum things, but we advise you to go through more about it. So Hamilton-Jacobi-Bellman here. Hamilton-Jacobi equations. Okay. So we will write a short form. What is Hamilton-Jacobi equations? So as I said, Hamilton-Jacobi equations is connected to what is called one of the most classical subject called calculus of variations. Calculus of variations. Okay. And as you know, in olden days, people formed many of the important problems comes from the minimization. You will see a lot of examples in this course. You minimize it and you study the minimization problems. It leads to a PDE called Hamilton-Jacobi equations. As I said, there is an advanced topic, Hamilton-Jacobi-Bellman. Okay, that is called Hamilton-Jacobi-Bellman. And this comes from what are called optimal control problems. Optimal control. So as I said, calculus of variations to minimize our trajectories, but in optimal control, the trajectories are determined by the control. So you apply control and the trajectories are designed, or you can change the trajectories based on the optimal. So it's a kind of one-player game, and there is a much more general notion and called Hamilton-Jacobi Isaacs equations. Isaacs equation. This comes from what are called differential game theory. Differential games. Okay, as I said, there will be multiplayer game. So it's not just one person controls the trajectory. Basically, there will be two or more controls, and there is a lot of literature in Hamilton-Jacobi equation thing. The thing is that there is what is called an associated value function. Value function associated to minimization problems. Associated to minimization. And this value function basically satisfies the Hamilton-Jacobi equation or Hamilton-Jacobi-Bellman equation or Hamilton-Jacobi Isaacs equation. As I said, you will see some of these things. Okay, and as I said, you will see more and more equations. So typically a Hamilton-Jacobi equation is a nonlinear equation of this form ut of tx plus h of t x u something like du. Du is the derivatives basically. Okay, du is the derivative with respect to u, du by dx1 etc. du by dx. We will not, as I said, is equal to 0. So we will not be studying in this generality, and I said that quite often value function need not be, you may understand what is value function later. Value function need not be smooth. Need not be smooth. And hence you have to interpret the solution in a weak sense. Interpret the solution in a weak sense. And there is a very general theory developed in the 80s, general theory by Crantel, Lyons. There are many people. So Crantel, Lyons, etc. So they developed a theory of viscosity solution. We will not discuss that here. Viscosity solution. And this viscosity solution is also extended to general nonlinear equations, not necessarily Hamilton-Jacobi equation. So we will not be studying this equation, study the special case. Special case where this does not depend on u, ut plus h of x du equal to 0. Okay, so there is no dependence, explicit dependence of t or u there. And more specifically, we will also avoid, so certain results we will do when there is an x dependence on this h, but more specifically, so we will be considering this very special case h of du equal to 0. And of course, there will be an initial condition. Okay. And this h is called Hamiltonian. H is called Hamiltonian. This is a terminology from Newtonian mechanics or classical mechanics. Okay, so that's what we are going to. So our main aim, as I said, derive Hoflach's formula, which we will do it in next class. Hoflach's formula, and then we will also want to study Euler-Lagrange equations. Euler-Lagrange is called EL equations. Okay. And as I said earlier, we will also see some sort of an transformation, which we will explain to you as we proceed further. Okay, and then maybe we indicate existence uniqueness. Okay, so that's what we are going to study. So let's look at this equation. Now recall equation ut plus h of x du equal to 0. This is in general as a nonlinear equation, but it's a special form of this nonlinear equation. U equal to u of tx is an unknown in n plus 1 variables. Okay, unknown in n plus 1 variables. Okay. So if you put this equation in a very general form, you can write it as f of t x. Okay, so that gives you n plus unknown. Then you will have u ut, then uxi for all I equal to. X is also a vector, where x is also a vector, n vector. So x equal to. So this is what you are having. So if I put notations here in terms of my method of characteristic, so if I introduce this notation ftx uz, okay, r p, this is where r is equal to ut and p is equal to your du. That means that is pi is equal to du by dxi. So this is a multi-index notation, 1 less than or equal to I less than or equal to n. Okay, so you see this will be of the form r plus h of xp. That's what xp is equal to 0. So since it's an n plus 1 equations, the characteristic equations consist of 2 into n plus 1 equal to 2n plus 3. A characteristic consists of 2n plus 3 equations. But this is a not very general second order equation. This is an equation you see in a very special form. You have that one, equations. Okay, so hence you don't have the explicit dependence of all the variables. So I will leave it as a small exercise. You can decouple to get 2n equations for xi of t and pi of t. The characteristic equation, you introduce a variable t, and initially you have a parameter, and then you can consider that tau variable will become the t variable itself. Equations as dxi by dt, this is your, so this I will leave it as an exercise to derive, is equal to, you equations you have dxi by dt is equal to dh by dpi, and then dpi by dt is equal to minus dh by dxi. Okay, so this is a 2n set of 2n equation. This is called Hamiltonian system. Hamiltonian ODE or system, Hamilton system. This is again have importance from classical mechanics. What we are discussing is a very general case, but when you have a special Hamiltonian, which is nothing but the Hamiltonian in classical mechanics is nothing but your total energy. We may give that example. So in compact notation, we will write it in this form. So we may not write it. So these are all for 1 less than or equal to I less than or equal to n. So you have 2n set of equations. So eventually we will be writing xi dot is equal to, the derivative is, let me not even. So we will write x dot is, x dot means x1 dot etc xn, that's equal to the derivative of h with respect to p. So we are going to eventually use this notation. So UCH is a function of x and p. So you are using that one, and your p dot is equal to minus dx of h. So this is a compact notation for the same representation. So we will be using this notation throughout this class. So I suggest you to go through these equations and derive this using the method of characteristics which we have explained to you in the previous PDE1 course. Or if you will be familiar with already such equations, you may easily get this equation. So you can derive that equation. So with that, now let me, before going to these equations, the connections, etc. will give, I want you to give some examples where you may not get existence or uniqueness. And then we will also explain to you one simple problem of a simple problem from the calculus of variations, if I have time this lecture, or we will continue with in the next lecture. Okay, so these are the things you should be able to derive easily. So let me start with an example. Okay, this is a very simple equation, mod du square, not mod du square. So let me do it in one dimension. So that's better, easy. So you have u prime of t. I tell you, we will use either prime or dot or du by dt, etc. thing. Okay, all represent the derivative. If it's a one variable thing. Okay, du by dt square minus 1 equal to 0. My domain is minus 1 to 1. Okay, and I want this conditions boundary value problem. U minus 1 is equal to u of 1 is equal to 0. Okay, so I will not be doing all the details, so you can actually work out as an exercise. I will give you the reasons, and it's a trivial exercise, means the claim, it's a claim. There does not exist any classical solution. There does not exist any classical solution. So you see, this is a very simple equation, and even such a simple equation, you are unable to prove the classical solution. It's a typical nonlinear problem. You see, that is, that does not exist u in C1 of minus 1 to 1, and since you have to interpret the thing and you need continuity up to the boundary, satisfying the equation. Proof is almost trivial, so I will not give the proof. You can prove it in different ways. You can prove it in different ways if you want it. One way you can apply if you want mean value theorem, because mean value theorem implies you see, u minus 1 equal to u1 is equal to 0. So there will be a point at which u prime is equal to 0. U prime of psi will become equal to 0 for some psi. So you can use continuity and all that results, and you can prove that if you want to apply this theorem. And but we have u prime is equal to 1 always, but u prime equal to 1 always. So what basically you can prove is that by continuity, this is one way. Another way can actually see that by continuity, you can actually see that this is another way. Okay, you can if u prime is a constant, continuity of u prime, because it's a C1 function, you can actually show that. So this is another way of showing it. Okay, implies u prime is either identically 1 or u prime is either identically minus 1. So you see, so you can't get a solution. So this typically says that you have a function, you want u minus 1 here, u1 here, and you want something like that. So you will have a somewhere you will get a 0. So you cannot have it means the slope is 1 all the time. So you can have. But interestingly, you see, suppose you relax. So this is fine. So if I relax a bit, suppose if I relax, what do I do? Look at this function now. So I will slightly prove something. These are the concepts which we are going to do it, but one here. So you have here. So I will put this thing. So that is 1 and minus 1 here. So you see. So here u prime is equal to 1. Here u prime is equal to minus 1. So this modulus of u prime for this figure, my u prime is equal to 1 except at 0. Except at t equal to 0. You see. Thus, this function u satisfies the equation except at t equal to 0. So you are getting a solution. So if you relax little bit, that if you get away that demand that u prime should be 1 all the time, modulus of u should be prime, then you have one solution. So in fact, if I relax little more, if I go like this, so if I go like this up to half and 1 like this is my u, and then if I do this way, and then suppose this is my v, then mod v prime is also equal to 1 except at 3 points. So if I try to explain a solution that and this u prime is definitely Lipschitz continuity etc., which is going to come. So if I am trying to relaxing my demand for a solution, that the solution is the equation should be satisfied except at finitely many points, then I will get a large number of things. So the relaxation produces a large number of solutions immediately. So this is the one way of relaxing. In fact, if I look asking for a solution which satisfies the equations almost everywhere, then you may be able to produce infinitely many solutions. You see. So the moment you try to relax a little bit on the concept of a solution, it's you are immediately you are getting a solution. So the existence is available, but it's possible that you may lose uniqueness. So let me now look into an example 2. So let's look into another example. Example 2. Here I am looking for my ut plus ux square. This equation is a little general, equal to 0 for t greater than 0 and x is in R. And I will have a initial condition u0 of x, the initial value problem. So this is an initial value problem, and I am putting u0 x is equal to 0. So immediately, trivially, u identically 0 is a solution. But I can define utx is equal to, okay, 0 if 0 less than t less than mod x, and I define minus t plus mod x if t greater than mod x, this is t less than mod x, and the other way, t greater than or equal to mod x. Okay, so can immediately see that 0 less than t less than mod x, you have this solution, so t greater than or equal to mod x, and you can show that indeed u0x, so this we can even define less than or equal to, so when t equal to 0, this is always less than or equal to mod x, equal to 0, satisfied. And so I will leave it as a small exercise. Verify that u is differentiable. U is indeed differentiable except on the line t equal to mod x. You see, except, and satisfies the equation, and satisfies the equation. Okay, that means it's a line. So in a so it's a two-dimensional t and x problem. So you are studying this problem here. Well, this is your x and t positive. You see, and you are defining something, so you get some t equal to mod x is. Okay, so you have your solution 0 here. So, and the line, so this line has the line mod equal to as the measure of the line is 0. Measure of the lines, segment of the lines, t equal to mod x is 0. That means that you get another solution. So that gives another solution except on a set of measures 0. Except on a set of measures 0. Further, u is Lipschitz continuate. Further, u is Lipschitz continuous. So, in fact, one will be able to produce many solutions later, not just one solution. You will be able to, we will see such a existence of many solutions actually later. Okay, and this is a completely a different solution from the trivial solution u equal to 0. Okay, so the one possibility, one possibility is to look for Lipschitz continuous solution. Look for Lipschitz continuous solution. The fact is that the solution, such solutions need not be unique. Such solutions need not be unique. So the problem is that how to pick the physically relevant solution. Physically relevant solution. Okay, and need additional conditions. Need additional conditions. So we will see something of this short in the, we will see some equations in this setup. Okay. So what we are going to do a third example which we will do. So I will start that. I may not be able to complete that one, and example 3, and then we will continue in the next lecture. So we will start the situation from here. Example 3. This is more relevant in the context of our analysis which we are going to discuss it here. It is that finite time exit problem. Finite time exit problem. So let me describe the domain here, and then we will do the thing. Okay. So finally, so let me set up the thing first. So you have a domain Q which is 0 to 1 cross minus 1 to 1, because understanding this problem is very important. So you have a domain here. This is one here. Okay, so you have a domain here. Okay, so this is your axis here. This goes to this axis here. Okay, so you will take 0 here, 1 here, minus 1 to 1. So this is your domain. So the points are represented by Tx. Okay, so the T is in this direction. This is the T variable. This is the X variable. So you look at any point here. So fix Tx. So typically fix Tx. So I'm going to describe a admissible set. First of all, admissible set. So I will do this one today, and tomorrow we will see the problem. Admissible set. So you will start with, so let me want to, what is the meaning of exit time? Exit time. So you're looking for a trajectory, xt. Okay. So you're looking for this trajectory, txt. Okay. This is what you are looking for, a trajectory. So you have a point here. You fix a point x here. So now let me use that. So you have a point tx here, and you look for a trajectory. This trajectory may go something like that. So it will reach here. So at t equal to 1, you exit if that trajectory. On the other hand, if you go here and if you reach here, so you are not reaching t here, so you have the exit time is your tau here. So it's the first time it is disappears. The trajectory can move something like that here and here. So you will have an exit time here. Okay. So it's clearly explained it in the book. So tau is the exit time. Exit time. Tau is the exit time that is the first time the trajectory leaves the domain. Okay, and AT is the set of all such trajectories. Set of all such trajectories. Such trajectories. Okay. And this we call admissible trajectory. on this thing, we will stay. So if for this case tau is equal to 1. So if any trajectory comes and leaves here, so tau equal to 1. So that's the time. So that it completes the path up to t, because t equal to 1 is the maximum time. So up to t equal to 1, it covers everything. So in that case, your exit time is 1. But it's possible that the trajectories will leave before that and hit the boundary. So, okay. So you are looking for the first time tau, for which the trajectory txt is within that up to t equal to tau, and tau is the first time, so tau x tau will be on the boundary. Okay, so I will continue. I will describe a minimization problem on this domain, what is called a first exit time problem, exit time minimization problem, and we'll continue this example, and with that respect to that example, we will actually solve that problem and see that actually we introduce what is called the value function, which I described. That's a minimal value with respect to tx, and then we will see that Vt satisfies Hamilton-Jacobi equation wherever it is differentiable. The issue is that value function or minimal value need not be differentiable. So I will stop at this stage and we'll continue the lecture in the next class. Thank you.